time to start the session. It is 4 o'clock. Caleb and Henry, how are you guys doing today?
Very good.
Good. How are you?
Caleb, can you hear me?
Is my microphone not working?
All right, Caleb, I saw that you turned on your mic, but I didn't hear anything. Man, that means I've had 6 classes today. 4 classes, the mic worked, and 2 of them they didn't. That is crazy. I don't get why they don't. But Henry could hear you. Oh, Henry, could you hear Caleb, or could you just hear me?
Can you hear me? Can you hear me?
That's so weird how in some classes I can hear, and some I cannot. All right. Well, I can't hear either of you guys. That is so strange. Why some classes work and some do not. All right, here we go. I guess it doesn't matter. I'm gonna have to do the class anyways. Let's see here. Where are my files here? This is week number 3, BC Calculus. Here we go. All right, last week we were talking about limits, limits of functions. I have a lot of limit problems, and then we were talking about continuous functions too, I believe. It's so hard when you're dealing with BC Calculus because we go through so much material all the time that it's like, man, what did we cover last week? All right, so in this review, you know, when you're doing limits, the first thing you should do is you should always just plug the number in. So if I plug 3 in here, let's see, I probably don't have my pencil turned on. If I plug 3 in here, I end up with 0 over, that would be 9 minus 6 minus 3, that's 0. So 0 over 0 means we have to do something else. Well, the number one thing to do is just to factor. So I'm just going to factor the top and bottom. So I've got x minus 3 over, what is that, x minus 3, x plus 1. So the x minus 3's cross off, so I'm left with 1 over x plus 1. Plug a 3 in there. I end up with 1 over 4 for my limit. Okay. Yeah, we are typing today. No question about that. Not me, though. Boy, if my mic didn't work, that would be something terrible. All right. Number number 2, if I did this problem, I'd end up with 0. Whoa, there goes my marker. I'd end up with, what is wrong with this thing? Huh. That's a crazy marker. All right, so if I plug 2 in here, I'd end up with 0 on top, and I'd end up with 8 on the bottom. Well, 0 over 8 is a perfectly good answer. That reduces to 0. So my answer would be letter B. All right? So just because the top is 0 doesn't mean that the whole thing does not work. All right. How about these two? What is the limit as x approaches 0 of the absolute value of x over x, and the limit as x approaches 0 of sine of x over x squared plus 3x? Give me an answer for those. All right. What is the answer? Letter B for the first one? Does not exist. I agree. Now, the second one, there's kind of a trick to it. Do you guys remember last week I said that, do you guys remember what the sine of x, what the limit as x approaches 0 of the sine of x over x is equal to? You guys remember that? What is it? It equals 1. Now I'm going to tell you some other kind of cool facts. The sine of 3x over 3 equals 1. The sine of 4x over 4 equals 1. the sine of 5x over 5 equals 1. Get my drift? That they're all equal to 1. So if I can rewrite this thing, so I'm gonna try to rewrite this thing, since there's a 1 up here. If I can rewrite this as the sine of x over x, that's just 1. It would just cross off, right? So, boy, if I factored the bottom, doesn't the bottom factor to x plus 3? Isn't x squared plus 3x the same thing as x times x plus 3? Well, guess what? This basically crosses off. It's 1. So all I have left now is 1 over x plus 3. When I plug in 0, I get 1/3. Cool problem. Ah, love that type. Okay. Any questions on that one? All right. Last week we also talked about continuous functions. Which of the following statements is or are true? Okay, so this is a piecewise function. So which one of those are true? Letter C. Letter C, 1 and 2. All right, so now if I was going to do this problem, this function is defined for all numbers except 1. So there must be something happening at 1. So I'm just gonna factor this, x minus 1, x plus 1 over x minus 1. So I know darn well that at x equals 1, there's a hole in my graph. My graph for this function is x plus 1, so it looks something like this. But at 1, there's a hole. That's what my graph looks like. Okay? Now, it's filled in at 4. Well, when I plug in 1 here, this is 2, so 4 is way up here. So this is what my graph looks like. This graph is this piecewise function. Okay? So it says the limit as x approaches 1 of f of x exists. Sure does. When I go towards 1, doesn't matter if there's a hole in the graph, it does exist. The f of 1 exists. Yeah, it sure does. F of 1 is right here. It's 4. There's no question about that. F of 1 is continuous at x equals 1. Not a chance. There's a hole in the graph. It's not continuous. So I agree. I think Caleb said that it was letter C. Very good. That's a tough problem. There's so many things going on in that problem. That is a very difficult problem for most students to handle. All right. Here's another one. It says, and f is continuous. So this is my function. And it says f is continuous at x equals 0. Then k must equal what? Right? So let's see if you guys get this one. So basically, this is not a continuous function. The top one's not continuous. There must be a hole in it someplace. So what we want to do is we want to fill in that hole. We want to make it a continuous function. I am looking outside right now, and the lake is like as calm as can be. I should be out fishing right now. Letter B, but with a question mark. That's not a good answer when you put a question mark next to it. All right, so what I'm going to do is I'm going to factor the top. So that gives me x minus 1. And then I can cross off top and bottom, right? Because that's how we factor if something's the same on top and bottom. So I'm really left with x minus 1 over 2, which is the exact same thing as 1/2 x minus 1/2, isn't it? So this graph is a linear function also. It starts at negative 1/2, it goes up 1 over 2, so it looks something like this. But at 0, there's a hole in the graph. How do I know there's a hole in the graph? Because I crossed off an x on top and bottom. That puts a hole there at 0. So I need to figure out, if I put 0 in for x, I get negative 1/2. So that is how I'm going to fill up my hole. So B is the correct answer. Yes, very good. That is definitely the correct answer. Nice job, Henry. Excellent. All right. This week, what are we dealing with this week? We're dealing with connecting infinite limits. We're also talking about limits and continuity. Ooh, you got a chapter test at the end of this week. Yay! All right. Now, we're talking about limits. What you learn, you're going to be connecting infinite limits and vertical asymptotes, connecting limits at infinite and horizontal asymptotes, working with intermediate value theorem. All right. I would be playing this video for you. However, I could not find it. Can't play it if I can't find it. Here is, this is a definition that most students don't understand. A horizontal asymptote is if you have a limit as x approaches infinity and that function goes to a number. That would be a horizontal asymptote. Now remember, horizontal asymptotes. Let's review what a horizontal asymptote is. If I have a function, that goes like this. Oh no, I still have my straight tool. If I have a function that goes like this, and then it levels off and it goes straight, this is called a horizontal asymptote. So let's call this letter A. So the definition here for horizontal asymptote, it says if the limit as x approaches infinity of a function is equal to b or a or whatever, let's call it b. So if this function keeps getting closer and closer to b, and this horizontal asymptote, then this is a horizontal line. So anytime you have a limit as x approaches infinity, and it turns out to be a number, not infinity, not negative infinity, but if it turns out to be a number like 10, then 10 is a horizontal asymptote. That would be a horizontal asymptote to that function, okay? So that is how you find a horizontal asymptote. If you're finding the limit as x approaches infinity, if it is a number, then you know that number happens to be a horizontal asymptote. And doesn't that make sense? Because if your function is going toward infinity and it goes to 10, that means your function has to be getting closer and closer and closer and closer. That's the definition of an asymptote. And that is a horizontal asymptote. Now, how do we find the limits as x approaches infinity? That's the question that we have to be asking, because there's three types of problems that you could have. No, that's not one. How do we find limits as x approaches infinity? There's three types I can give you, okay? So I can give you a problem like this. The limit, oops, better write these nicely so you can read them. The limit as x approaches infinity of x to the fifth minus 4x squared plus 3x plus 5 all over x to the fourth minus 2x to the third plus 4x minus 6. Okay, that's one problem. Then I could give you a problem like this. The limit as x approaches infinity, let's go x to the fourth minus 2x to the third plus 4x minus 6 all over x to the fifth minus 4x squared plus 3x plus 5. And then there's a third type problem I give you. The limit as x approaches infinity. And let's go 3x to the fourth minus 5x squared plus 6x minus 2 all over 5x to the fourth minus 3x plus 2. Those are the only three types of limit going to infinity that you could have, okay? Can somebody tell me what the difference of those functions are? Okay, what is, I mean, they're long, they're discussing functions, but what is the difference between all of them? Infinity, 0, and 3/5. You're giving me the answers now. Caleb, but what is, how did you find those? What did you look at to figure out what those limits are? Okay, what did you look at? Okay, there's something, when you're doing a limit problem, the largest exponent. That is absolutely correct. If you're looking at the largest exponent on top and bottom, that's going to tell you what the limit as x approaches infinity is, okay? and this is what and Caleb must have remembered this from last year. If you're going, the limit as x approaches infinity, if you have a big exponent over a small one, your answer is infinity. If you have a small over a big, your answer is 0. And if they're the same, let's, I don't know how we want to write that. Exponent's the same. Then it's the leading coefficient of the highest terms. So in this one, the 5 is bigger than the 4. So all I do is I do big over small. Oh, the limit of this one has to be infinity. Okay? Here, I have 4 over 5. So small over big. Oh, my limit must be 0. Here, the exponents are the same. That means I take the leading coefficient of the top and bottom number, and that's my limit. Boom. That is how you find the limit. As x goes to infinity, you just look at the exponents, top over bottom. Okay? Henry, does that make sense? Caleb obviously remembers this from last year. Henry, does that make sense? All right. So let's take a look. These two problems, okay? Letter A, the limit as 4 minus x squared, the limit as x approaches infinity, of 4 minus x squared over x squared minus 1. What is my limit? Letter D, -1 is correct. Because remember, we only look at the highest exponent. So I've got -1x squared over 1x squared. So I've got -1. That is correct. Well, let me ask you one more question off the first problem. Does the first, if I gave you this function, if I said f of x is equal to 4 minus x squared over x squared minus 1, and I said, does this thing have a horizontal asymptote? And if it does, what is the horizontal asymptote? Okay. Does it have a horizontal asymptote? I don't know what the graph looks like, but I can tell you if it has a horizontal asymptote. Yes. And what is the horizontal asymptote? Y. Thank you for putting y is equal to. The horizontal asymptote is y is equal to -1. Very good. It is a horizontal line. All right. Second problem, 4 minus x squared over 4x squared minus x minus 2. What is my, I could say what is my horizontal asymptote, or I could say what is the limit. What is the limit for this problem? Letter B is correct. Very good. So finding limits as x approaches infinity is super easy. Now, there are some that get a little bit trickier, but we haven't found any of those yet. Okay. The next one, what is the limit? Is 5x to the third plus 27 over 20x squared plus 10x plus 9. What is my limit? Letter A, negative infinity. Oh, it's going to negative infinity. I didn't even see that. Thank you very much. It is A, because it's going to negative. Okay? So it's getting to be a very big negative number. Good catch there. I didn't even catch the minus sign in front of the infinity sign. How about the last one? 3x squared plus 27 over x to the third minus 27 as x approaches infinity. Letter E should be 0, shouldn't it? Because the bottom exponent is definitely bigger than the top exponent. All right, now, a little bit trickier. Okay. 2 to the negative x over 2 to the x. Oh. Okay. As the limit as x approaches infinity. Letter C, 0. Is that correct? Okay. Now, if I was going to do this problem, I know that if I have a negative x up here, I can bring it down to the bottom. So I could rewrite this as 1 over 2 to 2x, can't I? So that means the top number is very small, The bottom number, this thing is getting huge. That's a really big number. So I've got a small over big, which is 0. So that's all you have. You don't even have to look at exponent. You just have to look at the top and bottom. If the top is getting really big, but usually it's just by looking at exponents that we tell that. Sometimes you can't. All right, how about the next one? The limit as x approaches infinity of 2x squared plus 1 over 2 minus x times 2 plus x. Letter B. Caleb says letter B. I agree. Because if you multiply this out, and you only have to multiply this part out, I don't have to do everything, because I know that this is going to give me my highest. So that's going to be negative x squared, and the top has 2x squared. So all I have to do is that's 2 over negative 1, which is negative 2. So yeah, it is correct. Very good. Okay. Ooh, these you have to memorize. Remember we talked about the sine of x over x? I gave you the graph. So you really should know. I mean, you don't even have to, because remember the graph looks like this, and it gets closer and closer to 0. So that's a bad graph. But the limit as x approaches infinity of sine of x over x is 0. Both sides. It's going to 0. Okay, so now we talk about infinite limits. So if you have a vertical asymptote, so basically what they're talking about now is if I gave you a problem like this and I said, okay, I want to know what the limit as x approaches 1 from the right is. Well, I know that this function looks like this. I know there's a vertical asymptote at positive 1. So at positive 1, there's a vertical asymptote. And my graph looks something like this. Okay. So if I looked at the graph and I said, okay, what's the limit as x approaches 1 from the right? Oh, it's going up, 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 up. So that's going to be positive infinity. If I asked what is the limit as x approaches 1 from the left, okay, well, that's going down, 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 down. That would equal negative infinity. So some of these, you have to be able to figure out where the vertical asymptote is. And being able to see the graph really does help on these types of problems. There's no real easy trick like the last ones when it was the limit as x approaches infinity. There's no real trick on these. You just have to know what the graph is doing at that point, and you have to know if it's a vertical asymptote or not. Okay, so infinite limits as x approaches a, values of the function f of x outgrow all positive bounds, then it's going to positive infinity. If it gets all negative numbers, it's going to be negative infinity. So this is just vertical asymptotes. Okay, and here is an example of vertical asymptote. It says, find the vertical asymptotes of the graph and describe the behavior f of x to the right and left of each vertical asymptote. Okay, well, here is 8 over 4 minus x squared. Well, I could factor this thing, and some kids would say, well, why are you factoring it? Because in order to figure out where the vertical asymptotes are, I really have to have this thing factored down. So this factors, I don't like the way this is written. I would just go negative 1, and then x squared minus 4. Ugh, marker, drives me crazy. Okay, so this really is negative 1, x minus 2x plus 2. So I know I have a vertical asymptote at positive 2 and negative 2. Okay, so there's a positive and negative, or there's a vertical asymptote at positive 2 and negative 2. And this is what the rest of the graph looks like. Okay, and I would not know that without graphing it out. There's no way. I could find the vertical asymptotes, yes, there's no question about that. Could I find, okay, here's the next question. So I just found the vertical asymptotes, right? What is a horizontal asymptote? And could you find that without the graph? I mean, looking at the graph, we can tell what the vertical asymptote or the horizontal asymptote is. Looking at the graph, what is the horizontal asymptote? 0, y is equal to 0, right? Now, could I find that if I didn't have the graph? Could I find that if I just had this equation right here? If I just had 8 over 4 minus x squared, could I find horizontal asymptote? Yeah, just find the limit as x approaches infinity. Exactly. Well, the limit as x approaches infinity, this is small number over big number, that is equal to 0. So yeah, the graph kind of shows that the limit is x equals 0, right? So yeah. And then if I wanted to find out what's happening, okay, as I go towards 1 from the right-hand side, negative infinity. If I go toward 1 from the left-hand side, positive infinity. If I go toward -1 from the, so you can see how you can find the answers just by looking at the graph. But without that graph, you'd have a really tough time trying to figure out what the limits are. Okay, so when you're dealing with verticals, usually you want to graph it out, and I have no problems with that. Okay, so here's a problem. It says the graph of f of x equals 4 over x squared minus 1 has. I want you guys to do this problem. Okay, one vertical asymptote. The y-axis is the vertical asymptote. The x-axis is blah 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 blah. What is my answer? What's the answer to that problem? Can you select multiple? Yeah, absolutely you can. You won't get it right, but you can. All right. First place I start on a problem like this, okay, is I always want to figure out the vertical and horizontal asymptotes, okay? So the horizontal asymptote, I think, is the easiest thing to find, right? Because horizontal asymptote, all you have to do is the limit as x approaches infinity. Well, in this problem, it's small over big. I know I have a horizontal asymptote at y is equal to 0. Okay, that's a horizontal asymptote. Now, to find the vertical asymptotes, I factor the top and bottom. Well, x minus 1, x plus 1. So I know my vertical asymptotes are x equals 1 and x equals -1. Okay? So I know that it has these asymptotes. So in letter C, it says the x-axis as a horizontal asymptote. Yes, it is, because that's y is equal to 0. Asymptote x equals plus or vertical. Yep, letter C. I'm going to stick with letter C, but you have to use a lot of math in order to come up with those answers. I mean, I love this stuff. It really puts a lot of the math that you've learned in previous math courses to good use. All right, here we go. This one is all yours. All right, give it a shot. A little bit tougher. All right, I kind of looked away. Henry, did you just say that the answer is C for this one, or is that for the last one? I should look away from the chat box. All right, so let's check it out. First thing, horizontal asymptote. No, that's the same. So my horizontal asymptote is going to be y is equal to 1/2. And now my vertical asymptote, well, I'm going to factor out a 4x on the bottom. That gives me, what is that, x minus 1? Okay, so let's see if the top factors out. Ay, ay, ay. I'm going to have to use the cheater method to factor this because it has a number in front of the x squared. So I'm going to go x, 2x Multiply the outer terms together, that gives me 6. What two numbers multiply to give me 6 that add up to 2? There aren't any. That means this is not going to factor, okay? So nothing's going to cross off, so my vertical asymptotes are going to be x equals 0 and x equals 1. No horizontal asymptote at plus 1/2. That is true, but no vertical. There's vertical asymptotes. No horizontal. Nope, I know there is. A horizontal asymptote at y is equal to 1/2. Yes. Two vertical asymptotes, 0 and 1. Oh, you guys are so good. I agree with that 100%. Nice job. Okay. All right, now we're going to talk about the intermediate value theorem. I do have a short video to watch to talk about the intermediate value theorem. So I'm going to throw that on right now. Okay, let's see here. I'm going to share an application. Share that. All right, so here is the intermediate value theorem. Put a recording.
Means for a function to be continuous, we can look at our first major continuity theorem, the intermediate value theorem. Now, before we get into explaining what it means, let's take a look at exactly what it says. If f of x is a continuous function on the closed interval ab, then for every d we pick between f of a and f of b, there exists a c between a and b, such that f of c equals d. Whew, that's a little complicated, but it's not so difficult if you take a look at what it means visually. We'll begin with the function f, which is continuous on the interval ab. In other words, the left endpoint is a and the right endpoint is b. Therefore, this height must be f of a, and this height must be f of b. Now let's pick some height in between those two, any one at all. I'll pick this one, and we'll call this height d. Now the only thing the intermediate value theorem is saying is that this value, or height, d, is going to cross our function at least once. Not only will it cross the function, it'll cross the function between the x values of a and b. And as you can see, it crosses the function right here, and we call that x value c. See how this ties in with the theorem? If we pick a d between f of a and f of b, and it relates to a c between a and b, that's it. That's all there is to the intermediate value theorem. If you don't quite understand it, well, let's take a look at a real-life example, and it'll become even clearer. As promised, here's a real-life example of the intermediate value theorem. On a website called thespark.com, they held a contest called the Fat Project. You've probably seen posters and billboards that say, lose 30 pounds in 30 days. Well, the Fat Project was an exercise to see if someone could gain 30 pounds in 30 days if they really tried hard. Here's one of the participants in that project. Her name's Nicole. On October 1st, she weighed 121.5 pounds, and her goal by October 31st was to reach 151.5 pounds. Here's her weight gain graph over that time period. I think you'd have to agree, it's pretty impressive. So let's take a look at the intermediate value theorem with this graph. As you can tell, on October 2nd, she'd already gained 6 pounds. That's only one day into the contest. Huzzah for Nicole. However, on October 28th, she had gained 22 pounds. Well, according to the intermediate value theorem, I should be able to pick any value between 6 and 22 pounds. We'll say 14 pounds. And I know that Nicole must have gained 14 pounds at some point on the graph between the 2nd and the 28th. Now think about it again. It makes perfect logical sense. If your weight on day 2 is 6 pounds heavier than you started, and on day 28 is 22 pounds heavier than you started, and at some point in between there, you had to have weighed 14 pounds more than when you started.
All right, that, in a nutshell, is the intermediate value theorem, okay? So it's one of those things that, you know, it just, to me, it just makes intuitive sense. Now I've got to figure out where I am on my slideshow here. We did all those slides. Intermediate value theorem. All right, so to me, it just makes real sense that that happens with the intermediate value theorem. The one thing you have to do is you have to make sure that the function is continuous. If the function is not continuous, it doesn't work, okay? It does not work if the function is not continuous. So the intermediate value theorem for continuous function is the reason why the graph of a function continuous on an interval cannot have any breaks. The graph will be connected a single unbroken curve. It will not have any jumps or separate branches. Continuous function. So here it says the value of c, find the value of c guaranteed by the intermediate value theorem, f of x squared minus x plus 9 on the interval from 0 to 5, such that f of c is equal to 11. Okay? So basically what they're saying is there's a value between 1 and 5 that f of c has to equal 11. They're asking you, what is that value? Okay, what is that value there? That it's going to equal 11. Now, is there any one of those answers that we could cross off? Okay, is there any answers that I could cross off if we really think about it? 0, right? 0 is not in my interval, is it? So 0, we could cross off right away. Boom. Oops. Since I went to that video, I have to come back and turn my marker back on. Okay, so that's not on my interval. I don't think we could use 1 either. I think when they're talking about an interval, it has to be between there, but I'm not 100% sure there, so we won't do that. Okay, so what is my value? And how would I find my value? Okay, what is our value? Set f of x equal to 11. That's a good idea. So let's go x squared minus x plus 9. Again, I'm using my pen the wrong way. Is equal to 11. Now this is a quadratic. In order to solve a quadratic, I'm going to set it equal to 0. So x squared minus x minus 2 is equal to 0. Let's see if this thing factors down. And so what two values multiply -2 to add up? So how about x minus 2, x plus 1? So my values are x equals 2 or x equals -1. Well, -1 is not even in my interval, so I can just cross that off. Can't happen. X equals 2. So the intermediate value theorem is a pretty easy theorem to figure out. You're just trying to tell us that there has to be a value in between there. I think this is a problem off the Khan Academy. It says let h be a continuous function on the closed interval 1 to 6. A few values of h are given in this table. Okay, so -5, -2, 2, -5. Which intervals must contain a solution to h of x equals 0? Okay, so on a problem like this, graphing to me kind of helps. I only need the first quadrant here. So at 1, 3, 4, 6. So at 1, we're at -5. At 3, we're at -2. Does it have to cross? Could this function cross at 0 and then come back down to -2? It absolutely could. Okay, it absolutely could, but it doesn't have to. And that's what we're asking for, is which interval does it have to? So then at 4, it's at 2. I know that in order to go from -2 to +2, you have to cross this axis. You have to have an h of x has to equal 0 someplace in there. And then I also have -5 down here. So we know that between 2 and 4, it has to cross here someplace. I mean, there's no answer around there. So I think that was 2 and 4, and this is 6 here. So in order to get back down to -5, it's got to cross that x-axis again somehow. So it looks like choose all the answers that apply. 1 to 3, no. That doesn't. I don't know where. Okay, so 1 to 3. Oh, this was 1 right here. Oh, this was 3, not a 2. So this is 3, and this is 4. So I know between 3 and 2 it has to cross, and I know that it has to cross again by 6. So, oh, my answers. I'm going 3 to 4. All right, B and C are correct. So it has to cross there. All right. That was the last slide for today. Pretty easy stuff today. I mean, the intermediate value theorem wasn't the biggie, but finding limits as x goes to infinity and finding vertical and horizontal asymptotes, that was the big part. Any questions on any of that stuff that we went through today? All right. And it should. I mean, none of the stuff that we've gone through so far has been new material. I mean, as I said, AB and BC Calc are pretty much the same class until we get a little bit farther in. All right, you guys have a great week. If you have any questions or concerns, please never hesitate to email me, okay?